let's look back again at table 3. So the first variable in table 3 is this SAT score of the school, right? And so you can think about the SAT score of the school as a measure of like how good the school is or like how elite the school is. So schools with higher SAT scores, average SAT scores are more elite schools. And so if the coefficient on that is positive, what that's saying is that schools that are better schools or that are more elite schools are going to provide higher earnings for the students. That's not the student's own SAT score. The student's own SAT score is the student SAT score divided by 100, which is the second one. And so it's like, there are two benefits. So it's like, okay, what's the benefit of you going to a school where on average your peers are smarter and the school is a better school? And what's the direct effect of like your own kind of like intelligence is measured by just your SAT score, right? So we can think about the SAT scores of observability. And so in the first column, we see that you could see that going to a school that has an SAT score that's higher by like 100 points is going to increase your earnings by 6%, right? So that's the relation of that coefficient. Now, look at the things at the bottom. So average SAT score of the schools that you apply to, 1 additional application, 2 additional applications, etc. Those are supposed to capture your unobserved ability, right? And so the SAT score is the observability. Unobservability is like, think about it as how ambitious are you? Like how much have you prepared? Unlike a student that's going to be applying to a lot more schools, maybe the student is somebody who wants to say, look, I got into all of these schools, I'm really smart, or what have you, right? And so in the first basic column, we don't control for those things. In the second column, we control for the unobserved ability, which is proxy for using these things in the bottom here. And notice what happens to the coefficient on school SAT score. So the coefficient on school SAT score, remember, is going to capture what's the effect of going to a better school on your wages, right? That effect goes from being positive to being negative. But it's insignificant because the standard errors are like really low, right? So the t-stat here is going to be less than 2. And so the basic point is if we don't control for unobserved ability, it seems like the earnings for somebody that goes to a school where there's a higher SAT score is actually higher, right? That's what it seems like. But once we control for unobserved ability, what we find is, in fact, that coefficient is statistically indistinguishable from 0. And it's not the case that the person is benefiting from going to the more elite school. It's actually that the person, him or herself, is just a more able person. We just were not able to measure this unobserved ability, which is kind of the innovation of this paper. It's like, how do you use application behavior to measure unobserved ability? Are there any questions about that? Who understands that? Okay. Does anybody have any questions? Okay. The other thing too to look at as well is, so let's look at the coefficient on, let's look at the coefficient on black. And so what you can see there too is for the 1998 cohort, that's going to be positive in the basic case when you don't control for unobservability, right? But even after you control for unobservability, it's still going to be positive. Now that coefficient is not statistically different from 0, but it's like a 4%, like a 4% increase. And so this is that final result that although the effect goes away for like school quality, it still seems that minorities are benefiting from being, or at least African Americans in this later cohort are benefiting from going to more elite schools. So I want to talk you through in the time that we have left. So you guys have this sheet here. So this is a paper from Hoekstra in 2009. I'll just check this out. And so he has data on a flagship school. let's call that theta star, right? So basically, if your SAT of person I is greater than theta star, then you're admitted. If your SAT is less than theta star, then you're not admitted. Right? And the key idea here is going to be to look at what's called the C of theta star, and this would be theta star plus 10, theta star minus 10. So these guys here are going to be not admitted. These guys here are going to be admitted. Right? And so these guys are admitted to the flagship. I should actually put that to flagship. And these guys are probably going to go to like a non-flagship, right? Because they're not admitted at the flagship. And so we can see how this policy is going to affect the probability that they are admitted to the school. And we can also see how it's going to affect their wages, because we're going to have wages, we're going to have data on their wages going forward. And so if you look at figure 1 here, what you will see is that for people that are below the threshold, so these are the negative values, so this is going to be what's your SAT score minus the threshold. And if that value is negative, that means that your SAT scores are too low. They're admitted about 5% of the time. Right? Does everybody see that? What about for folks who are just above that threshold? Like how much percent of the time are they admitted? So somebody that's just above, so for someone that's just below the threshold, like to the left of that 0 point, what's the probability with which they're admitted? You can just read it off from the graph. Say it again? 8 to 10%. And for somebody that's just to the right of the threshold, meaning that they just have a marginally higher SAT score than the threshold, how much more do you think? Yeah, about 50%, right? And the size of this discontinuity is actually around about 0.4. So so just by going from an SAT score that's, let's say if this threshold was 1,000 points, just by going from 990 to 1,000, the probability of admissions goes up by 40%. But do we think that someone that has an SAT score of 1,000 is that much smarter than a person who has an SAT score of 990? It could just have been that that person was distracted for a microsecond, or they just tied their shoelace, or they didn't have breakfast that day. I mean, this is a really small difference. So the whole idea is that when we compare two people on either side of this discontinuity, that they're very similar in terms of their unobservabilities. Because in terms of their observability, they're very similar. We're not comparing someone who has like a 500 versus a 1,500. Okay. Now when we look at the second plot, figure 2, what we see is that there's also a jump in wages that happens as well, right? And that jump in wages is about 10%. And so if you're just to the right of that threshold, you're more likely to go to a flagship university, and you have higher wages too. And so we can use these two facts to get around this issue of unobservables, right? Effectively, what we're saying is that somebody to the left of this discontinuity with a 990 SAT score is a very good counterfactual for somebody that's to the right of this discontinuity who has an SAT score of 1,000. Does that make sense? And so we could just look at, well, what's the difference in their wages, and what's the difference in the probability that they go to this elite flagship school, and what's the difference in the wages as well too. And we can attribute a lot of the difference in the wages right there to the fact that the folks to the right of the discontinuity went to the flagship school, the folks to the left did not go to the flagship school. Does that make sense? And so we can estimate a return to going to flagship. That is equal to the change in wages over the change in the probability of attending flagship. So that's just going to be 0.095 divided by 0.8. which is something like 0.24. And so going to this flagship university is going to increase wages by around like 20%. And so this is another way that you can get around this issue of finding the right counterfactual, is you can have some kind of a rule where the probability of being treated changes discontinuously, or changes by a great amount, just as you go across that threshold. And then you look at people at opposite sides of that threshold to provide counterfactuals to each other. And then you can look at what's the difference in the outcome, in this case is wages, and what's the difference in the probability of going to college, which is you want to find out what's the effect of going to a flagship school on wages, and we can just do the ratio of those two effects to get what's the returns to going to a flagship school. So this is called a regression discontinuity design, and this is actually like a pretty good way of getting the returns to college as well too. It's called a regression. So effectively we compare individuals on opposite sides of the admissions threshold to estimate the returns to attending a flagship school. And you can use this in a lot of other contexts, not just for attending a flagship school. It could be for attending, it could be used in a lot of other contexts, but this is just looking at this particular technology used in the context of the economics of education. So that is it for today. I will send you, please read the Dale and Kruger paper. I'll also send you a couple other papers too. So like the basic setup for the course is going to take more of this format where we're going to look at papers that examine important policy questions, and we're going to go through what is the policy question, how do they use economics to answer the question, is this answer convincing, and a lot of the empirical work is going to focus on are we able to overcome issues of endogenous to make sure that the unobservables, what we observe is not correlated with what we don't have. So thank you and have a great day, guys.